how do we do this in the most responsible way moving forward? Our next session is focused on three speakers that come from The Ohio State University and Nationwide Children's Hospital, and really show a little bit in some very short presentations of the type of work that's ongoing on a regular basis at The Ohio State University. I think our faculty, our staff, our students are doing incredible work, and we have incredible opportunities to move that forward. And so we are absolutely thrilled today to have Doug Danforth, an associate professor in the Department of Obstetrics and Gynecology, who's going to talk about natural language dialogue systems using AI and machine learning. Sema Candemir, a research scientist in the Department of Radiology, who's going to talk about some image analysis, automatic detection and classification of diseases, and medical image analysis. And then Jennifer Hefner and her team, which is going to talk about deep learning models for pediatric patient risk stratification. So this is just a kind of a touch of the flavor of activity going on. The poster session that follows this afternoon is another opportunity to kind of see the breadth of what's going on in translational science, AI, and machine learning at Ohio State. And certainly the facilitated table discussions are places where we can take those further in the near future. So I'm going to turn it over to Dr. Danforth. Thank you to all three of our speakers who will follow one behind each other, and we'll have some opportunity for a few questions at the end. Doug.
Thank you. Good morning, everyone. I'm going to talk about a couple of natural language dialogue systems. One will be a machine learning system, and one will be a human learning system. And it's going to be more of a practical than a theoretical discussion this morning. But our application for using dialogue systems is to create virtual patients. Our virtual patients are avatar representations of human patients that our students can use to practice their history-taking skills. They're conversational. You can talk to the patients, they can talk to you, and generally they understand what you're asking them. And we have a variety of different sort of platforms for the virtual patients and uses of the virtual patients. We have a web-based, which is a chatted or typed conversation, and that's important when we talk about how you design a dialogue system to manage that type of conversation. We have a life-size version in the Clinical Skills Center that's a spoken conversation, and when we developed that, we were using Dragon Naturally Speaking. This was several years ago before cloud-based speech-to-text was available. And now our primary application is as an iPad version. We push the iPad app to our students, and it's a spoken conversation. We use cloud-based Watson for dialogue, for speech-to-text. And we currently also have a virtual reality version. You put the headset on, you're virtually in the room with the patient and conducting the encounter with the patient that way. So when you're designing a natural language system, there are some things you need to think about. You need to think about what's your input types or spoken. How are you going to understand the questions? Are you going to use a rule-based or a machine learning system? And then a little bit of what your output is going to be. That's important for our conversation, and our system may not be important for yours, but it is a consideration in terms of what you want your system to respond, how you want your system to respond. So input type, if you're using a chatted or typed conversation, those are kind of unique in the sense that the questions tend to be very succinct. People tend not to type really long, elaborate questions, at least our students don't. Their conversations are shorter, but spelling errors are something that you have to take into account if you're going to use that type of a system. There are autocorrect options available that help. That'll take care of many of the more common ones, but if you are in our domain, we have some pretty specialized words, and if the students or the healthcare providers misspell those words, it can make the dialogue system, can present challenges to the dialogue system. If it's a spoken conversation, it's quite a bit different. The questions are a lot longer, the conversations are a lot longer. You don't need to worry about spelling errors because your speech-to-text system is not going to send you back misspelled words, but it is going to send you back a lot of incorrect words. It's going to misunderstand what you say. And here's an example. This is an actual example from our application. So I'd be probing seems to help. So that's good. And so you you said this began about 4 to 5 years ago. You had another episode. Well, A, that's not even a question, so I'm not sure what we do with that. And B, I'd be probing is supposed to be ibuprofen. But Watson, when it was trying to understand that, made that I'd be probing. And so depending upon the type of the dialogue that you're working with, speech to text can introduce some pretty amusing errors. And then if you're doing a spoken dialogue, students will tend to lump several questions together. Are you generally happy with your life now, your house, your job? Well, which one of those? The difference in our conversations than the typical application like Siri and Alexa, they can understand a wide variety of inputs, but you can't have a conversation with them. They basically understand one thing at a time, and you can't have a nuanced conversation. We're trying to do something completely different. Our domain is very narrow, but the conversations are very deep. So the first approach is not a machine learning approach, it's a human learning approach. Pretty much I'm the human who learned how to do this. It's a rule-based or pattern matching, sometimes called a handcrafted approach. Basically, our domain is narrow, so we're only talking about the questions that a doctor asks a patient. So we focus on those. That's a limited domain. Basically, use a software program that matches patterns. So I wrote about probably now about 6,000 rules to manage that conversation using the specifics of the software program. The software program does some things. It does canonization and parts of speech tagging and all of that. One of the most important things it does, though, is pronoun resolution and keep track of where you are in the conversation. In our domain, we have to know exactly what you're talking about. When a student says, "When did that happen?" we have to resolve that pronoun, and we have to know, are you talking about when did you take a medication? When did you hurt your back? When did you previously see the doctor? All of that is more difficult to manage, and you really can't ask Alexa or Siri, when did that happen? Because pronoun resolution is generally not a feature for that. And our accuracy rate with just a rule-based approach generally tends to be about 70 to 80%, depending upon a variety of factors. Depending upon whether the input is typed, we do better when it's typed than it's spoken, how complex the case is, whether it's a difficult history or a simple history. And one of the most important things is your audience. First, your students ask a lot of crazy questions, and so trying to manage those crazy questions compared to a third or fourth year student that is going to ask focused questions that are easier to manage. So one of the things we wanted to do early on was to see if we could improve our dialogue system with a natural language, a more contemporary machine learning approach. And all of the work with the machine learning and the CNN approach is done with my colleagues at the Departments of Computer Science and Engineering and Linguistics, Dr. Mike White, Eric Foster-Lucier, William Schuler are the primary faculty members, and then we have a variety of graduate students who've worked on this, David King, Evan Jaffe, Liefeng Jin, and primarily the graduate student Adam Stiff did most of the engineering and programming for this system. So when we trained the CNN, we used a word and character-based CNN to identify the questions. Basically, the CNN almost always does worse than ChatScript. I've been writing patterns a long time. I know what the questions are. We're pretty good at that. And the CNN doesn't really have, in our domain, very many questions. There's not a big data set. Machines are good at learning, but they're pretty dumb. They need a lot of data to train the machine. And so for a number of years, the CNN was always worse than the handcrafted approach. But when we looked at the types of questions that were being missed, we saw that they were different. The CNN was better at some types, pattern matching was better at some types, And when we had a human retrospectively go back and classify those, we could get a dramatic increase in accuracy. So then we created a classifier, a binary classifier, to choose based on the types of questions that each one got right. And it was not as good as the human, but still gave us a pretty big increase in accuracy. And so we wanted to see, could we, this was all done on retrospective data, could we create a live system that would do all of that in real time? And this was largely developed, again, by Adam. So last fall, we had all of our students interview Mr. Carlos Martinez. We had about 200 students, asked about 12,000 questions. And the first thing I'll draw your attention to is how well the speech-to-text did. This was delivered on an iPad. The students were doing this at home, watching TV. They were doing it at Starbucks, wherever, so not a controlled environment. Watson didn't do too bad, got about 70% of the input questions almost exact. Got about 90% acceptable. A human could understand what Watson was saying. And it just munged 10% completely and would just provide gibberish. In general, the results were the same. Overall, our accuracy was lower. These are now spoken conversations and not typed conversations. But in general, ChatScript gets about 70 to 78% correct. The CNN, always a little bit lower. The chooser, when it chooses between the two, again gives us an increase. We didn't get quite as dramatic an improvement on the live system. And there are some things that we did wrong when we were developing that, and we're going back and working on that. But one of the things we're focusing on now is the speech-to-text side of things. So Watson got it right in this situation about 70% of the time. But when we've looked at other systems, Watson is really untrained, not that good. Microsoft is about the worst. The word error rate for our domain anyways is about the worst. Google is about the best. Google's a little more difficult for us to integrate into the system, so that's why we focused a little bit on Watson. Untrained, Watson about the same, but you can train Watson using a couple of different models based on your data set to make it better in your domain. And in fact, when we train Watson using our data, we can get it to be almost as good as Google and some of the others. So what we're going to do now is go back and use the train speech-to-text system to see if that improves our accuracy. We're using our new data to train the CNN. The more data you have, the better the analyzer. And so that's kind of where we're going in the future. The last thing I'll just talk briefly about is your output. What are you going to do? How are you going to have your system talk to you? Typically, most everyone will use a text-to-speech. Siri and Alexa, those are $1 million voices, probably $10 million voices. They sound like they do. Most people are not going to have access to those really high-quality voices. And you're limited also in terms of how your system responds. We needed some specific applications. We needed voices that had a specific accent, and we needed voices that had a lot more inflection. So we decided to actually pre-record all of our answers. That's very time-consuming, but you get a very realistic voice, and it can help you with specific applications that you got. So in summary, using a variety of different natural language systems, machine learning systems, human learning systems, our virtual patients, pretty good at answering questions. One thing I didn't talk about, they also categorize and classify all the dialogues and give immediate feedback to the students, and they can actually grade the encounter as well as a human can grade the encounter. Dialogue systems can be fairly simple, rule-based pattern matching approaches or sophisticated machine learning. The rule-based systems require handcrafting rules, but they're good to start with, especially if you don't have a lot of training data. Machine learning systems can be actually much more robust, but they require a lot of training data. And actually, hybrid systems can actually work pretty well. The 4 finalists for the Alexa Prize last year to create a conversational AI all used a hybrid system for their approach to manage the dialogue. And then depending upon the application, there are a bunch of modern cloud-based systems. If you're just trying to create a simple Q&A sort of system, some of those might actually be a little bit better. And that's our support, and I'll turn it over to next speaker.
I'm Sema Candemir, working as a research scientist in the Laboratory for Augmented Intelligence and Imaging. Thank you for the organization. I'm very happy to be here. In this presentation, I'm going to present automatic detection and classification of diseases in medical image analysis. I'm also going to present our laboratory and mention a few of our studies. This is going to be a very general talk, no technical details, but I'm happy to discuss more during the event after the presentation. Sorry. How I'm going to the next slide? Sorry. How I'm going to the next slide? It's not going to the next. This one. Okay. I'm going to start with a general definition. Computer vision is how machines see and understand images and videos. And in this discipline, we are developing algorithms to automate tasks that humans can do. And these are a few examples. Target tracking, that target could be human, car, or military vehicles. Face recognition, emotional recognition, image reconstruction. These are problems that computer vision algorithms are trying to solve. In medical image analysis domain, we are developing similar algorithms, we are employing some of these algorithms developed in the computer vision discipline, and we automate tasks. We apply these algorithms to the medical images, and we automate tasks that doctors can do. For example, understanding radiology scans or grading level of severity of the disease can be two examples. For example, in this study, it's conducted in Stanford University. Researchers train a very large neural network algorithm with a very large data set released by NIH. And they detect pneumonia from the chest X-rays as good as a radiologist prediction results. We repeat with my previous colleagues in National Library of Medicine, we repeat the similar study to detect pneumonia in pediatric chest X-rays. For grading level of severity example, this study is very interesting. They train a neural network system with a very large fundus images, and the algorithm is able to grade the severity of the diabetic retinopathy as good as ophthalmologists. But how machines make a decision? In conventional way, before all this deep learning popularity, we were collecting data, obtaining annotations, reading images, and there is an important stage here, feature engineering, and it directly affects the performance of the whole system. And what kind of descriptors that you need to choose also depends on the problem that you are working on. For example, if you are developing a system to classify X-rays with the cardiomegaly, cardiomegaly is basically heart enlargement, and the main difference between normal one and the abnormal heart is the volumetric difference. So you are going to need a descriptor which gives you a shape information. But if you are developing an algorithm to detect tuberculosis or pneumonia, the manifestations of these diseases causes textural deformation on the appearance of the chest X-rays. Therefore, you are going to need a textural, a descriptor or combination of descriptors which gives you more discriminative textural features. So after you get these features, you train a machine learning algorithm, and based on your definition, metric definition, you measure the performance of your system. But right now, deep learning is the high trend, and with the advances in GPU technology and the massive amounts of data, the computer vision systems designed with deep neural networks started to provide more accurate results than the conventional approaches. But what is the main difference? This is a very rough illustration, and as you could see, in the data-driven approaches, there is no feature engineering stage anymore. You don't need to worry about what kind of descriptor you are going to choose. If you have enough annotated data, and when you provide this data to the neural network algorithm, your algorithm will learn the most discriminative features during the training process. So roughly, this is the main difference, we could say. Now we get rid of the feature engineering stage, and all we need is to provide all the data to the system. But is life much easier now? Unfortunately, no, because there are some challenging conditions. Training a deep neural network architecture requires a large amount of annotated data, and if you are working in the medical imaging domain, obtaining annotation is very expensive. For example, if you are in the computer vision domain, let's say you are developing an algorithm for a realtor company, automatically classify the houses from the house images. All you need is to go to a hosting service and download images and do the crowdsourcing options to get some help for the annotations. But how about if your task is developing a system to detect stenosis on coronary computed tomography angiography? Who is going to ask for the annotations? Obviously, you are going to need an expert in cardiovascular radiology. So collecting annotation is a very expensive process. And let's say you convince a doctor to help you for the annotations. Do you have an annotation tool to collect these annotations? Because annotation is very time consuming, and you don't want to, you want to use your doctor's time as efficient as possible. And these are the other problems. What kind of neural network architecture you need to choose? You have to deal with the hyperparameter optimization. If you are working in the images, medical images or normal images or videos, you are going to deal with a large number of learnable parameters, and if your data is scarce, you're obviously going to deal with the overfitting problem. And all this process in the imaging domain is computationally very expensive, so you are going to need graphical processing units. But there are some solutions to mitigate some of these challenges. For example, if your data is scarce, you can use pre-trained models. There is a very large data set outside. It's called ImageNet, which contains 1.2 million general images. And there are architectures which are trained with this very large data set. And the earlier layers of these architectures knows to low-level features like lines, circles, which are still useful for your own problem. And basically, you employ these architectures with their ways as a base model for your problem, and then fine-tune your architecture with your limited data. In this way, you can take advantage of larger neural networks and obtain good results with your limited data. And there are also augmentation techniques that you can use, or you can introduce some regularization techniques to deal with the overfitting. As in Laboratory for Augmented Intelligence in Imaging, we are doing research and development and building algorithms for the clinical medical imaging analysis problems. And we are collaborating with clinicians for problem definitions and clinical importance of that problems. Also, we need annotations. And these are the projects we are working on right now: coronary artery screening, early Alzheimer's detection, brain metastasis, hemorrhage detection, and bone fracture detection. This is the project that I would like to show you as an example. Recently, with my colleagues, we developed a system for coronary artery screening for abnormal detection. And the system automatically classifies the vessels as normal or vessels with stenosis. System is based on a three-dimensional convolutional neural network. It's a supervised system. And we trained the system with vessel volumes extracted from normal patients and patients with stenosis. For the annotation, my colleague developed a clinician-friendly user interface. That interface has similar capabilities that our doctor actually using during the clinical environment. And our principal investigator, who has 33 years of experience in cardiac imaging, spent a lot of time to scan, to go over the almost 500 scans and manually annotate more than 600 cardiac vessels. And we still need to increase the images to obtain good results. So we also apply some augmentation techniques by basically rotating the vessels around their center lines. And right now we are getting good results, around 90% accuracy, but it is improving. We are applying more pre-processing techniques. We are trying to improve our data. You can get all the technical details in our reports that we are sharing, actually, preprint copies of our webpage. And these are the other projects that my colleagues are working on. This is, for example, very interesting. It not only classifies the X-rays, it also detects the bone fracture location, as well as provides the severity of that fracture. This is also another interesting project, brain metastasis. They first apply a circular volumetric filter to reduce all the noises in the whole brain volume. And in this way, they're able to detect even the subtle metastasis regions. And so this is all. As a summary, we are a very new group, and we are looking for collaboration and grant opportunities. Thank you very much. I guess our new talk.
Hello, everyone. So my name is Jennifer Hefner, and I'm an assistant professor in the Division of Health Management and Policy in the College of Public Health at Ohio State. And my colleagues are here with me today, and they are from Nationwide Children's Hospital and the Ohio University. We cross institutions, and we'd like to thank Simon Lin, who's our senior collaborator, who works across these institutions also. We're going to talk to you today about using deep learning in risk stratification. So our objectives with this project were to develop a deep learning model approach to pediatric patient risk stratification, and that we could use to improve methods of risk stratification. And we also wanted to foster a collaboration between Nationwide Children's and Ohio State College of Public Health. The goal was to bring machine learning to a policy audience. So the group that has been doing this machine learning and risk stratification work at Nationwide Children's can publish in the clinical informatics journals and get that known among other people who do your types of research. The question is, because we feel this is really policy relevant, how do we get this information out into a policy audience also? So those were the joint aims of this project. What we did was use a deep learning model to develop a predictive algorithm for future healthcare utilization. We used claims data. We'll tell you a little bit about that in a minute. And then we used our model to assess the predictive validity of our models against some other commonly used risk stratification models in a small pediatric data set. So why do we care about risk stratification? And this is kind of a policy and management question, which is where my interest comes in. So healthcare reform is pushing value-based purchasing, and what that basically means is that for a group of patients, the healthcare system or providers will be rewarded for the outcomes of those patients. So keeping them healthy is a main goal to save costs and to improve patient outcomes. So if you think of the patients under a healthcare insurance or health system, you can think of it as a triangle, and most of the healthy people don't cost much, and they're at the bottom. And as you go up the triangle, let's see if I can use there you go. As you go up the triangle, people are a little bit more at risk. If you go to the top of the triangle, they have multiple chronic illnesses and advanced critical illnesses. These people right here are 75% of the admissions. They're a huge percentage of the cost, but they're a small percentage of the population. So risk stratification is trying to understand as soon as possible who your patients are that are at highest risk, that are that you can coordinate their care and hopefully lower costs and improve outcomes. So the challenges in pediatric risk stratification is that commonly used models use predictive regression models, and that's an analytic challenge because of the sparse, multidimensional types of data that comes from insurance claims. And then state-of-the-art risk stratification models that are currently used by healthcare systems and insurance companies are traditional grouper models. They're labor-intensive. They were developed with a lot of domain and expertise knowledge, and they were also developed in adult populations. So there's poorer predictability in pediatric populations, and they're also not as agile and able to adapt as your patient population changes. So deep learning, as we saw in the last presentation, can sort of leverage the complex data that's available in health information and electronic health record systems. And you can use predictive analytics to do an unsupervised learning approach, and that can be with automatic feature engineering. So the application of deep learning to patient-level risk stratification is a new avenue. It's showed some promise, but our work, we understand, is the first to apply deep learning to a pediatric data set and attempt to perform patient risk stratification. The study population for this, the study sample for this work was from Partners for Kids. This is a large pediatric ACO, one of the oldest and largest in the country. As you can see from the graph of Ohio, patients come from 34 counties in Ohio. That's over 330,000 lives, and there's a large group of people who work within the ACO to try to understand how we can properly risk stratify our patient population to target them with care coordination interventions. So I'm going to turn it over for a moment to my colleague, Xianlong, who developed this deep learning model, to tell you a bit about the model, and then I'll come back and tell you about sort of the results and implications.
After pre-processing, we have about 120,000 kids, and the predictive model we use is used in 2014, 2015 as the training data sets, and 2015, 2016 as the testing data sets. And can we go to the next slide? And for those of you who who are not familiar with the claims data, here's an example from the PFK data sets. And as you can see here, a patient is represented as a sequence of medical visits. And each visit contains a set of medical claims, like the asthma, the urgent care, the procedure, medication, and the corresponding attributes, like the place of service and the cost. The model architecture. So we first represent the patient as a set of medical codes. Here, the 0, 1, 2 represent the frequency of the medical code. We call that a raw patient vector. And then we project the raw patient vector into a latent space that represents the patient and then concatenate with the DI, which is the demographic information. That's a little bit too fast, but it's fine.
Oh, sorry.
We're still talking about the left-hand side. And then the right-hand side, we're using the similar terminology to project a visit vector into the latent space, and then the idea is trying to predict what the patient will have in the next visits, the medical codes, the medical events. And that button?
Yeah.
Okay. So the training objectives are to learn medical code representation that's good at predicting neighboring codes within the same visits, and learn patient representation that's good at predicting the neighbor visits. And this is a slide that shows that we can learn some meaningful representation of the medical codes, medical visits, and patients. As you can see here, we can definitely see some clustering effects of different kinds of medical codes. Like the left-hand side, we have asthma, depressed, and seizures that are kind of separated into in the 2D dimensional space. And then the right-hand side, the high-cost and low-cost patients are kind of separated as they're different, and that kind of show that we can learn meaningful representation. And after we obtaining the meaningful representation, we use it to predict patient hospitalization in the subsequent year. Okay, thank you.
So this is our first bit of results. We looked at the area under the curve as our primary evaluation metric. And up here, you can see 6 different models that we use. The first was a logistic regression using the demographic and utilization variables that are in the electronic health record. And that the area under the curve is 73%, and the little bit smaller area under the curve was using the clinical classification software, which is group-related medical codes that is traditionally used for risk stratification. And then the DXCG intelligence is another proprietary model that's used by PFK currently and other health insurance and health systems to do risk stratification. And then the last 2 lines are the deep learning model that was developed by our team. So that showed a 73.5% area under the curve, and then when you added demographic and utilization variables in to the deep learning model, we saw 75% area under the curve, which is the highest under these different models that are currently in use. So slightly higher with fewer manpower inputs into the system. So another analysis we looked at is the financial impact of using this model. So the deep learning model can more accurately predict high utilization patients, and by predicting a risk for hospitalization and then looking at costs. And small improvements in the model performance can have a big impact. So while the area under the curve increased in performance was small, it led to millions of dollars difference in the ability to predict utilization. So this is illustrated up here. We used both models to select the top 1% and then looked at their combined actual cost. And the deep learning model had costs of $31.1 million for the top 1%. And then the current standard in use by PFK and others has predicted $26 million. So the deep learning model for the 1% of high cost individuals, the ACO could potentially influence an additional $5 million in costs compared to their current risk stratification modeling. The strengths of this study was that we used an unsupervised learning approach that reduces human effort. It's also more agile to allow for frequent updates for constantly changing, improving model performance. And you can train the model on specific population cohorts, so you can get specific within the types of patients served by your organization. Limitations of the current study is a small pilot data set, so we're definitely gonna need to rerun this model on lots of different variations of data. One of our inclusion criteria for the patient sample also led to some limitations. So we selected patients who were continuously covered under the ACO for 3 years, which could be a different type of patient population from their total patient population. So sensitivity analyses are needed around that. The policy implications. So we want to improve the ability of pediatric ACOs specifically and other managed care organizations generally to do preemptive planning for financial risk. The ability to improve future diagnostic prediction can lead to better assessment of provider performance, better patient mix considerations when you're talking about pay for performance metrics, more realistic resource planning if you can identify more accurately the higher cost patients, and that can allow for the very practical care coordination and the types of interventions on complex patients that keep them healthy and reduce adverse events. So our references and our paper is available online in the American Journal of Managed Care. You can see below here, all of our other co-authors from PFK and Simon Lin, our senior contributor. And if you have any questions, we're happy to take them, or you can look up the paper and email any of us, and we'll be happy to talk to you about it.
I think we have just a moment for any questions, if anybody has for any of our three speakers.
I don't know where they went.
Yeah, if you can go to the microphone again, please. There's one on that side, there's one on this side. Only because we have people who are listening to it live streamed and it's difficult to hear the questions.
Hi, a question for the last group of speakers. Very nice talk, thanks a lot. I just wanted to ask about bias and transparency, right? So the deep learning models are even more inscrutable than logistic regression. So it seems like there's a real risk if you're talking about rationalizing resources that issues of bias, say if, you know, associations with the zip code, if there are patients in those zip codes that traditionally have underutilized resources, that could be propagated forward unfairly. I imagine you're probably familiar with these issues. Can you just say a little bit about how you're thinking about that?
Definitely. Do you want to go first? Or
Okay. So definitely that is a limitation for deep learning, and on the other hand, it kind of, our approach is really taking in everything and then identifying those that are grouped in under that high-risk category. And we do have, so this is not entirely just data-driven. So obviously, with our PFK partners, they have care coordinators assigned. There are certain ways that you can actually evaluate and try to gain insights from those ones that are selected by the deep learning approach.
So I think the one thing to add is we did have these discussions with the reviewers of our manuscript. And if you look in the manuscript, we do have a discussion about future directions. And I think one important one is to, as we include social determinants of health data into electronic health records, and specifically patient-reported surveys and outcomes, we can then incorporate that into the deep learning model. So right now, a lot of the features of that you're speaking about are not reflected in electronic health record data. But as that becomes more common, and there are certainly in the larger EHR vendors that are starting to collect those types of social determinants data, we can include that in the modeling, which is what's so interesting about the deep learning being agile in that sense.
Others? Well, thank you to all three of our speakers. Very exciting work, and thank you for sharing with us. Yeah. Do I need an operator?
Yeah, just turn it on.
Oh. Sorry. Now you can hear me a little bit better. Sorry about that. So I think, as many of you know, to have any large initiative across multiple institutions requires a village. And our next speaker is Dr. Morley Stone, our Senior Vice President for Research at The Ohio State University. When we originally started to talk about opportunities for bringing together a university-wide and nationwide children's hospital initiative, we reached out to several groups to begin these conversations. The Comprehensive Cancer Center, and Matt Ringel certainly was instrumental in that. The Office of Research in the university, leadership at Nationwide Children's, and of course leadership across the OSU Wexner Medical Center. And we really brought together and started to think about ways of how could we reach across not just the health sciences colleges, but broadly across all 14 academic colleges at Ohio State, because each of us brings some unique insights and expertise to really bear on enhancing human health by employing these kind of new computational models and approaches. And Morley was in at 100%, and he's going to talk to you a little bit about kind of the university-wide vision, opportunities that we have moving forward, and ways that as a community, as a scientific group, that we can have an impact not only on those health issues that are the greatest concerns for the citizens of our state, but in fact nationally and globally, and working collaboratively with the NIH, NSF, and others. So Morley, thank you so much for coming. Sure.
So thanks, Becky, and I did want to stress when she first brought up this topic, I certainly was indeed 100% in. Let me give you right up front, and there's no slides, I'm just gonna talk to you a little bit. No PowerPoint, death by PowerPoint here today. But it's really getting to the issue of just how important this topic is, and having watched this now for over 20 years in different settings, the reason that I jumped at it from a research opportunity for this university is just how important it can be in terms of really harnessing strategically the breadth of this institution to really demonstrate thought leadership that's clear and definitely needed in this field, just not only in the medical area, but in a profound number of areas that I'll touch on today a little bit. So early in coming here, I talked about one of my priorities being around human-machine teaming. And I soon learned from the quizzical looks that I was getting around the room that human-machine teaming, or HUMT as it is abbreviated at times, didn't have the same enterprise understanding that it did in my previous employer. And for background, human-machine teaming in that terminology was our way of addressing the fact that as a system became smarter, and again, make no mistake about it, our systems are becoming smarter, we had to shift our thinking away from seeing a system as a tool and instead seeing it as a teammate. And this was acknowledging a future in which decision-making was going to be shared. And again, if you think about that, and all of a sudden you begin to boil it down to this paradigm of shared decision-making, immediately that should begin to clue up the fact that we need, as a research community, to make sure that we're reaching out to fields like the social and behavioral sciences, as an example, where we can begin to actually tie into the scholarship that is occurring in those fields. And especially, let's think about some of the topics that have already come up this morning. Topics such as trust, transparency, bias. These are things that are absolutely essential to the success or failure of these techniques, and yet oftentimes are we actually pulling in the desired scholarship partners that we need to adequately address this. I love the question that came up this morning about vendors that come to you with specific tools that they want to tell you, that they want to sell you, that'll cure whatever ails you in your particular software issue and diagnostic issue. What they don't want to tell you in the conversation that they don't want to have is if that model is based on a neural net architecture, they cannot tell you how that model arrives at its conclusion. And that has been a very inconvenient truth, if you will, of a lot of these model developers. And it has spurred action on the part of the federal government in terms of starting large-scale programs like explainable AI and the absolute imperative of understanding how we can begin to develop explainable models. So as we all appreciate in here, the data that we, and I'll use that royal we in that sentence, that we are collecting is beyond human comprehension, hence the necessity of harnessing machine intelligence and machine learning. And what we mean to reflect in that royal we is the fact that it is broad and it's getting broader every day in terms of the different fields that are being impacted. So as an example, I've watched this migration occur recently in the field of material science, and it's hard to overstate just how profoundly this is changing that field as one example. For example, the growth of carbon nanotubes with useful electrical and mechanical properties in the past has been very much a hit or miss operation, often relegated, if you will, to the special recipes used in a particular materials fabrication lab. ML approaches to this material science problem has totally revolutionized the growth conditions that are used in carbon nanotube synthesis and has sped up discovery by several orders of magnitude, as one example. So we are in the midst of watching this permeation take place in medicine, from underlying precision medicine to drug discovery to the development of patient monitoring, and machine learning is rapidly becoming as foundational as the underlying biology or chemistry. So just how transformative? And as we've heard through some of these talks, early on, AI was seen as a potential diagnostic tool, especially when applied to medical scans. NIH, for example, was an early funder in looking how a system based on machine vision can outperform a physician. And immediately we start to see some of the inherent problem here. Remember what I told you about shared decision-making. Immediately, the tendency was to reduce this to a Ken Jennings on Jeopardy playing Watson, or reduce it to AlphaGo playing the world Go champion. But what we fail to recognize, and I think what the realization is occurring, is that that has to change. You have to get back to this idea of how can these tools become a decision aid, not a decision maker. And so when we start to look at this, we have to adopt this mindset of how can an AI ML system comb through data beyond human capability, identify best candidate options, and bring that forward to a human decision maker. That is exactly the tact that IBM started going down after Watson, if you will, left the stage with Ken Jennings, and turning that into a decision aid. So modern medicine, indeed modern systems engineering, is based around underlying statistical model approaches, hence the gold standard of randomized, double-blind, placebo-controlled studies. But I think where we're starting to see this could turn medicine on its head is, what if N is equal to 1? The amount of data that we take from one patient with the explosion of the omics revolution is turning his or her own data sets into staggering size and proportion and is growing every day. What if each treatment, each intervention was tailored to the individual? That vision is what's changing medicine and will only be realized through the full community adoption of AI and ML techniques, both warts and all. So new research opportunities are reflecting this reality, especially from the federal government. You can look to last year's $2 billion plus announcement from DARPA, or NSF's National AI Research Institutes from the federal government. If you haven't seen it, I would urge you to look at the federal government priorities that were released at the end of August, both from the Office of Management and Budget and the Office of Science and Technology Policy. You will see AI and ML all through that document, as well as healthcare priorities. And it's important to understand that when these documents get released by OMB and OSTP, they're released to federal agency heads. So this is the guidance that individuals like Francis Collins look at when they begin to structure the solicitations that come out of NIH. And so I call your attention to, for example, just as representative examples, just on October 1st, there was a workshop out of NIH on artificial intelligence healthcare, from prevention and diagnostics to treatment, that both could be attend in person or online. How many folks in the audience participated in that? Great, we've got 2. So again, and I think it just calls to the fact, especially for this audience here that is really geographically based here largely in Central Ohio, to continue to look for these coming solicitations that are coming out and will just continue to increase. Currently looking at a call out of NIH as well, out of the Division of Health Informatics Technology on artificial intelligence, machine learning, and deep learning. So in my view, this pairing of AI and ML coupled with researcher and physician-based decision-making is the most transformative effort underway in biomedical science and medicine, and I'm excited to see where this workshop output takes us, and look forward to following up with Becky and Matt. Thank you very much.
Thanks, Morley. So one of the ways that I said that we really moved these initiatives forward was connect, convene, catalyze, and enable. And one of the ways that we catalyze is to incentivize teams to come together. Teams of clinicians, basic scientists, computational scientists, computer scientists, engineers, people who work in biosensors, people who work in public policy, to address those kinds of scientific issues that they find most compelling and important to be able to improve human health. I hope all of you picked up front this little flyer, which is a flyer regarding the pilot initiative that we actually announced in late September, but we want to bring back to your attention today. And this is a pilot specifically linked towards artificial intelligence and machine learning and translational science and in human health. There's a letter of intent due on December the 10th. There's a red cap, so if you go to the CCTS website, which since I live by Google, so they know everything about me, but you can Google CCTS, and the good news is we bump up first to the group and look for this. You can actually upload. It's a very short letter of intent to look at that, and then invited applications for full applications. And the full application deadline is January 30th. This does require teams across more than one college or between Nationwide and Ohio State, because part of this really is to do that preliminary work, to do some of those excitement. And it covers everything from methodologic development all the way through actually studying a scientific hypothesis. So we really hope that this will be an opportunity. One of the ways of trying to build these teams is to also create networking and other types of activities. And so the only thing between you and lunch is me talking a little bit about the facilitated table discussions. So one of the things that we started actually at our last CCTS meeting was the opportunity for people who had interests that kind of convened around certain areas to meet over lunch, to be able to start to have discussions of that. And these are discussions that are going to be facilitated around certain types of questions and ideas to move things forward. We actually have a scribe in each of the rooms, and there are a list of, I think, 5 different facilitated conversations in 5 different rooms, all up on the 3rd floor. So the first of those in the area of thinking about AI and ML in terms of personalized medicine, which will be in the Brutus Buckeye room. Go Bucks. The second is in imaging and AI, which will be in the Hayes Cape room. The third, clinical trial design. So really facilitating more effective clinical trial design using AI, which will be in the Rosa Alibori room. AI and genomics, certainly an area that's actually near and dear to my heart and my own personal research interest, which is the Suzanne Scherer room. And then lastly, AI and drug design, which will be in the Tanya Rutner room. So if you follow from here, lunch is available. There's box lunches across the hall. You know, please feel free to go to one of those rooms that really are an area that strikes your interest. We have both scribes and facilitators who will actually work within those rooms, and we'll be actually posting some of the outcomes, some of where you think are the areas that we should be investing on developing out further. If none of those are areas, we invite you to take the opportunity to talk to people you've never talked to before, to reach out across the aisle, to find people where you might be able to find synergistic or in fact complementary expertise. And then we'll all reconvene at 1 o'clock for a keynote speaker, Dr. Christopher Austin, the director of the National Center for Advancing Translational Science, and kind of my boss, and who's going to talk a little bit about catalyzing translational science. One last housekeeping thing. Please, those of you who are Twitter competent, which I am not, I just troll Twitter accounts that have to do with OSU football. But you know, our tweet and our hashtag is hashtag OSU ASM19, and make sure that you put out there one thing that you learned, one thing that was provocative, one thing that we can really share about for people to think about the next generation, where are the opportunities in AI and machine learning. Thanks, and have a wonderful facilitated lunch.